Well, good evening, everyone.
Hi,
Welcome.
Jerry.
Hi. Welcome to week 9 weekly review session of business analytics. How has your week been going?
It's okay. I'm in North California, so we have a lot of rains. Um,
Oh, you're
Starting
not. Which
today.
state are
Yeah.
you in this moment?
No, I am in the Bay Area.
Oh, I see.
Yeah.
Well, hopefully it's not too cold. I heard that in Northern California this winter there has been a big issue of um, too much snow, and
Yeah,
some people living
no,
in the mountains were stuck in their home.
correct. And don't ask about our electricity bills because of the heater.
Oh, really? Oh, okay. All right. I won't ask, but it sounds like it's lots of payment. All
Yeah.
right. How about other students? Are you okay with this week's learning? Any outstanding questions? This week, we built on what we learned last week from confidence interval to hypothesis testing. In fact, they are related, and we will see very soon how they are connected.
So I was working on the homework, and
Okay.
I'm not sure if I got the first question right. I I just wanted to clarify if my null hypothesis definition is correct.
Oh,
I
I see.
am
Was it you that sent an email earlier asking about how the null hypothesis should be constructed? It appears in an email question I got, uh, some student had difficulty forming the null and alternative hypotheses, which
yeah,
is
I
a
was
critical
asking about
step.
the two-tailed, yes.
All right, without further ado, let's take a look at our weekly homework. And so we can understand together what's required and how we can form how we can take correct steps towards the right result of the analysis. So first, I would like to remind you that I sent a announcement in the class about the review of my review, about a feedback of my review session. You will get this link in the announcement where you can fill out a evaluation form. Alternatively, you could also find the feedback form link on my shared note of the business analytics review session. You will be able to find a link to the note if you go to Canvas modules and the TA office hour. Once you open the tab, you will see that the review session notes is right linked on this page. All right. So I will appreciate it if you fill out the feedback form. In our week, we will learn two major parts. One is on hypothesis testing. There are several steps we need to follow to complete a hypothesis testing question. And associated with that, there's some learning regarding statistical significance. It may not be exactly what you think it is. So there are some caveats we need to learn about. And the second step part or component of this week's learning is on p-values. We use this often in both academic research and also professional projects. However, there are misconceptions about p-values. That's why we should review the fundamentals about p-values. And there are also some common myths about p-values. And with that, we practice how p-values is constructed and calculated and what it means in regression models that corresponding to problem 3 in our week. And during the process, I will also show what's the link between confidence intervals and hypothesis testing. They are actually almost equivalent. And I also supplied some material beyond the course where you can learn more about the p-values and also common misunderstandings about p-values. And there's also p-value hacking, where we can derive significant results out of no patterns. And it's like a thing in academic research. So don't always trust what we read. And there are also advanced testing techniques where we can test a combination of all hypotheses. All right. Now my plan is to start looking at each of the homework questions. Before that, do you have any questions about the fundamentals of statistical testing or p-values? All right, now let's start taking a look at the homework questions. This week we have 3 problems, and 2 of them are on statistical testing. And the last one is regarding p-values. It's also statistical testing, but in the context of regression. Here, in problem 1, we have a sample, and we know the sample mean and the standard deviation. Now we need to answer a question regarding some claims. And in part B, we will change the significance level and do the same, do a test to address the same question again and find whether there's any change. Did you run into any difficulty in the procedure, and what was it?
So the hypothesis that I assumed, right? I wanted to have an average drone delivery time greater than equal to 30 minutes as null hypothesis. So it's left-sided. My thing is that I am getting a don't reject the null hypothesis. So I was not very sure because I made that assumption so that I can reject the null hypothesis.
Oh, I see. The result that you got was not the basis of determining whether the procedure was correct or not. So it's common or acceptable, at least, if we don't reject the null hypothesis. So finding non-significant results is okay. However, what matters is whether the null hypothesis is formed correctly and whether the procedure followed is correctly done. So let's start from the procedures so we understand what correct procedures we must follow. Well, first, we need to determine the test type. As Rochana just mentioned, she was correct in terms of selecting which tail should be used. But let's take a look at both components about what I mean by determining the test type. This matters in terms of which distribution we need to choose. Particularly in our case, it's limited to a choice between z-test or t-test. The z-test is relevant or appropriate if we know the population standard deviation. Take a particular node at the population when I mentioned, so that z-test is only okay if we know the population parameter in terms of standard deviation. For example, if we take a look at our problem, could you tell me whether we know the population standard deviation or not, given the information reviewed in the question words?
We only know the sample standard deviation.
Okay, that's correct. That means we do not know the population standard deviation. In that case, we would have to use the t-distribution. The t-distribution has a fatter tail, so that if holding everything else constant, it will give us a larger p-value than a z-test would. So we sacrifice some significance because we do not know the population standard deviation. That's why that's what I meant by that. This determination between z-test and t-test is not determined by the sample size. Do not confuse of using a central limit theorem here. It's not really relevant. What's relevant is whether we know the population standard deviation. It could be also expressed as population standard errors, or population variance, or population standard deviation. All right, now we need to determine whether it's a two-tailed or one-tailed test. If one-tailed, whether it's left-tailed or right-tailed. This is suggested by the alternative hypothesis. So in our case, because the claim has this direction, like 30 minutes or less, so it's less than or equal to 30 minutes. It has a directional sign in it. That's why it's a tailed test. However, to determine whether it's left or right-tailed, we would have to form the hypothesis directly. So could one of you give a tentative answer in terms of how you formed the null and alternative hypothesis? I would like a volunteer to announce how you form both of the hypotheses.
I'll take a shot, but if anybody
Great.
else wants to answer.
Go ahead, please.
Yeah, so for the alternate hypothesis, I used what we want to see, right? Which is less than 30 seconds.
Oh, okay. Hold on there. I would disagree. So here, to determine what should be put on the alternative or null hypothesis, it's usually that what we desire to find is retained in alternative hypothesis. Note that these two components, null or zero hypothesis, and the alternative or the H1 is a complete set. So there can be only two results. Either the null hypothesis is true or the alternative hypothesis is true. There cannot be any further options at all.
Yeah, so I put less than 30 in the alternate and greater than equal to 30 in the null.
In that case, we will find exactly the opposite p-value as what we would find as what I have here.
Oh, sorry. I put greater than equal to 30 in null.
So here, let's pay attention to how I made the choice. As I just discussed, what we usually put in the alternative hypothesis, that's what we will get if we reject the null hypothesis, would be the desired result we want to find. So here, because the original claim was that the delivery time, the average delivery time is 30 minutes or less. We want to find evidence against such claim, right? So this evidence, that's what we desire to find, has to go into the alternative hypothesis. That means if we go against the original claim, that the average delivery time is greater than 30 minutes. Once we are clear on that, we would put the remaining on the null hypothesis. So it would be the original claim that the average time is less than or equal to 30. Let's take another practice. In problem 2, we
So
also
Jerry,
face
one question. If we take null hypothesis less than equal to 30,
Mhm.
right? That's what you're suggesting.
Yes.
Will it not be right-tailed?
This will be right-tailed because the alternative hypothesis has a greater than sign.
Okay.
Now, let's take another practice in terms of forming the correct signs in alternative and null hypothesis. In problem 2, we also face this hypothesis forming question. We know the average, the sample mean and the standard deviation. And we also know that there's a 95% confidence interval for the population average length. Okay, so in part 1, we want to test whether the average length of boats is 6 centimeters. And so how did you form the null and alternative hypothesis in this case?
Null was equal to 6.
Well, that sounds correct.
And
So in this test, yeah, the reason why we do that is we want to put the significant result or the desired result we want to find in the alternative hypothesis, so that rejecting the null hypothesis would derive a significant result. So here, let's think for a minute what significance here means. So here, the significance means that the average length in bots that we draw from has an underlying population mean that's different from 6 centimeters. Because here we want to find a statistical difference, or otherwise understood as a statistical difference. So we want to find the difference, and this difference, if it's different from 6 centimeters, then we would find a significant result. That's why we put the alternative hypothesis as the average length of boats is not equal to 6 centimeters. And with that, the null hypothesis would mean that the average length is not different from 6 centimeters. So the mean value is equal to 6 centimeters. Any questions in hypothesis forming? We have just decided what to choose and what to put on the alternative versus null hypothesis.
So what is required will go on the alternative. That's what you're saying?
As I indicated earlier, we want to put significant result in the alternative hypothesis.
Okay. Okay. So
So
for
for
the first
example,
question, then going back to the first question,
yeah,
for the alternative hypothesis, because the question says delivery time purchased averages to 30 minutes or less, that 30 minutes or less is on alternate hypothesis.
incorrect. I would put that in the null hypothesis, because if we want to find a significant result, then the significant result means that the original claim, the CEO claim is wrong and or incorrect, so that there's a significant difference from the original claim. That's why we put the opposite to the original claim in the alternative hypothesis.
Okay, difference, opposite of the original claim. Okay.
Yeah, so here you could know that this stands for significant result. Or here, the null hypothesis, this stands for no effect or no difference or non-significant result. Oh, right. How about other students? Are you all clear with how what we choose to put in the both parts of the hypotheses? If yes, then the next we would simply make a note in the report about the chosen significance level. In part A, in problem 1, it'll be 0.05. Then we also need to understand what parameters we are testing. Understand that first, the very reason we do all these hypothesis testing is that we want to infer from a sample about the unknown population that we could not all sample. For example, here in problem 1, we only sampled 50 deliveries and try to understand the average delivery time of all deliveries that we did not really sample. That's why we need to do hypothesis testing. Otherwise, if we were only concerned about these 50 deliveries and not at all concerned about all the other possible millions of deliveries, then we would never have to do any hypothesis testing, right? Because we know perfectly what's going on among these 50 deliveries. However, we only have limited result that we do not know all the rest millions of deliveries made. So that's why we try to make an inference from the sample to the population. That's why it's also very important to understand or define the population parameters we're testing. Here in problem 1 and 2, they're all about the population means. However, in other real world examples, this population parameter could be anything. It could be, as I listed in confidence interval last week, anything we could build confidence intervals for, we could also do hypothesis testing. For example, in addition to means, we could also test hypothesis or build confidence intervals regarding difference intervals, regarding population variance or ratios of variance between two populations. We could also test the quantiles, such as median or the first and third quartile. We could also test median absolute deviation or skewness or kurtosis or proportions and correlation and regression coefficients or R-squared, many things, etc., etc. So the hypothesis testing is not limited to population means. And when choosing this parameter, understand that it must be a variable. The research question is rarely about the subject or participants or the sample size. We're testing a parameter like a mean value. All right, now the next step would be calculating test statistics. Before then, any questions? All right. In this step, we would have to use the statistics Excel prepared by the professor. So let me find it. Any questions while you or difficulties when you used the Excel sheets to find the test statistics?
No, the Excel was straightforward, just the definition of the null hypothesis.
Oh, okay.
Yeah.
Glad to hear that from you. How about other students? Did you have difficulty using the Excel sheet?
No, I'm in the same boat with Roshana. Just identifying the null and alternatives for me.
Oh, great. All right, let's see whether you calculated the test statistics correctly. So here in problem 1, we already determined first, we need to use a t-test because we do not know the population standard deviation. And we also formed the null hypothesis to be the original claim and alternative hypothesis to be the opposite of the original claim, so that the population mean is greater than 30. Then we also know the significance level. So we put the information here in the hypothesis test tab. Note that there are several blocks. The first part is sigma known. That corresponds to we know the population standard deviation, because we do not know that when we address problem 1, so we should not use it. Instead, we should use this block 2, where the sigma is unknown. Sigma here stands for population standard deviation. That's why if it's unknown, we should use this sheet. However, if you encounter questions regarding population proportion tests, we should use block 3. Or here, if the test is regarding population variance, you would have to use block 4. Let's focus on block 2, so because we do not know the standard deviation of the population, but we want to test about the population mean. All right. While I walk through this, please supply the statistics I would need. What should I put as the population mean here?
30.
Great. That's the correct answer. Because this population mean stands for the reference population mean. This would come from the null hypothesis. Because here, what's the null hypothesis is the original claim made by the CEO that the average delivery time is 30 minutes or less. That's the reference mean value we want to test against. That's why it's put in as the population mean. So it actually stands for reference population mean. Significance level is 5%. How about the sample mean? What should I put as the sample mean value here?
32.1.
32.1. All right. How about the sample standard deviation?
5.4.
Great. These are supplied in the question itself. How about sample size?
50.
All right. Now we have 3 columns calculated. Left-tailed, two-tailed, and right-tailed from the leftmost and to the rightmost columns. Which of these 3 columns did you use to derive the results?
Well, the sample standard deviation is 5.4. Oh, you put 5.2.
Oh, did I? Okay, sorry. Slight mistake. Yeah, that's why it's very important to read the question clearly. From a previous homework, I've seen that some students had all the procedures correct, but some of the values as input was made incorrect. That totally disturbed the ultimate results. All right, this should reflect exactly what the results would be, but which of these 3 columns did you use to derive the answers to problem 1?
Right-tailed.
Yeah, you're right. So this is clearly shown to choose between these 3 columns. Just pay attention to the null and alternative hypothesis to see whether it matches with what we formed earlier. Because in this question, in problem 1, as we practiced earlier, the null hypothesis is the average delivery time is equal to or smaller than 30. And alternative hypothesis is the average time is greater than 30. That's why in the in these three columns, only the rightmost corresponding to right tail test matches with what we want to test.
Jerry, can I ask a quick question?
Sure.
Is it safe to phrase it this way? If the alternative hypothesis value is greater than the null hypothesis value, that makes it right-tailed?
No, it's not. The answer lies here. I think it's quite clear when we use two-tail test, right? But it seems it's less clear what makes it right or left-tailed if it's a one-tail test. So that's why I supplied a hint here. If you remember this one, then you would make the right choice in other cases. So if the alternative hypothesis has a greater than sign, then it's right-tailed.
Okay, thank you.
As it shows here, because the alternative hypothesis has been greater than 30, it has a greater than sign. That's why it's right-tailed. All right, so with this, let's take a look at each of these calculated statistics so we understand what we are testing against and what each of these test statistics suggest. So here, the critical value is a critical value of t-value. We want to compare our test statistic against. This is calculated, as the formula shows, based on only two parameters. That's the significance level and the sample size. As it shows, it's not related to anything else. Once we confirm the significance level and sample size, nothing else will change the critical value. And it's calculated based on the t-distribution as an inverse. If we click the hint on the link on the function name, we know that this calculates a value as the quantile. Well, sorry, I guess I clicked the wrong one. Okay. The inverse t-distribution, it returns the two-tailed inverse of the student's t-distribution. That's why if we are concerning not two-tailed, but one-tailed, specifically right-tailed, we would have to double the significance level. So that this significance, this critical t is calculated based on actually a significance level of 0.1. That's the double size of what's written here. All right. This is the reference t-statistic, but what is our test t-statistic? Here it's measured as 2.74. Note that no matter whether we are using one-tailed or two-tailed test, the test statistic remains the same. This is quite in contrast to what happens to critical values. Although both critical value and test statistics are all some t-statistic, but they are calculated differently. The critical value is calculated, as I showed earlier, based on significance level and sample size. Instead, the test statistic is calculated based on several more parameters. It's related to both the population and the sample mean. It's also related to the sample standard deviation as well as the sample size. If we go to this case, well, because they are the same, right? So they use exactly the same formula. It's calculated as the difference between the sample mean and the reference population mean. so that they are actually estimates of two different populations. Although here one is referred to as a sample mean, the other is referred to as population means. But we need to understand that they are actually estimates of two different samples. The first sample, they are estimates about two different population means. The first population is what the sample stands for. That's the true underlying population that we do not have full access to. And the second population is the reference population, that what the original claim made by the CEO stands for. So we're actually comparing two populations using the sample estimates. And this difference in population difference estimated from the sample mean difference is going to be divided by the standard error. This standard error is calculated as the sample standard deviation divided by the square root of the sample size. That's exactly mirrors what we did last week when we calculated confidence interval. So that means this test statistic is nothing but a ratio, a simple ratio. The ratio is the difference in two population means divided by the standard error. And then with that, we calculate a p-value. This formula is somewhat complex, but here it stands for if we build a t-distribution with the degree of freedom of 49. That's the sample size minus 1. Then we take a look at the proportion at the probability that this t-value is greater than the test statistic. That's what it stands for, if the null hypothesis is true. And because this p-value is so small that it's close to 0 and smaller than this significance level, that's why the decision we make would be that we reject the null hypothesis. We reject that the mean is smaller or equal to 30. So we find significant evidence that the average delivery time is greater than 30 minutes. That completes the procedure. Less than the implication we need to make. We can practice it very soon. But any questions regarding the procedures in using this hypothesis test sheet? All right. If we are all clear about how to calculate the corresponding critical value, as we just calculated, it's a critical value of t. And the test statistic, it's a t-value calculated as a function of the sample mean and the reference population mean and the standard error. Given the information from the question, then we made a decision that we reject the null hypothesis. The reason here can be two parts. We could either refer to the p-value if it's smaller than the significance level. Here, this 0.004 is smaller than 0.05. That's why we reject the null hypothesis. Or we could achieve or derive at the same decision if we look at the test statistic. Because this 2.74, actually 2.75, is greater than the critical value, which is 1.68. That's why we would also reject the null hypothesis. Note that here, the critical value would be different if we choose between left-tailed or two-tailed or right-tailed tests. So it makes a very important difference between these three columns. Although the test statistics stay the same across these three types of tests. And you will also find that the p-value also varies greatly. We could actually find that the left tail test and the right tail test p-values would sum to 1 if you collect both of these two cells. And this two-tailed p-value is 2 times of the right-tailed test. Note that the two-tailed p-value would be 0.008, whereas the right-tailed test would be 0.04, right? So this two-tailed p-value is 2 times of the smaller one between these one-tailed tests. So pay particular attention to which of these three columns we should use. All right. Now it comes to the last part. Given the decision we just made that we reject the null hypothesis, what implications should we derive from it? Could one of you try to interpret what it means when we reject the null hypothesis?
That the delivery time did not decrease to 30 seconds.
Excuse me, I don't follow. It doesn't sound right. There's no decrease because we're not testing any, temporal trend. And here, if I were to answer this question, the implication I would derive if I reject the null hypothesis that the average delivery time is smaller or equal to 30 minutes, is that.
But Jerry, sorry.
Could I complete my answer before you ask another one? Another question, I mean. So if I reject the null hypothesis written as here, it would mean that I found the significant evidence against the null hypothesis. Or I could also say I found the significant evidence that the average delivery time is greater than 30 minutes. So that's what you really find in published articles and professional project reports, saying that if you reject a null hypothesis, that we find evidence or we find a significant difference based on the data. Yeah, so what are some additional questions?
Yeah, so my only confusion is because the problem statement says that company plans to develop a drone that would cut delivery time. So cut delivery time means decrease delivery times, right?
Oh, I see. Okay. That would be a reasonable concern. However, it's not really relevant in our question, as what we formed as the null hypothesis and the alternative hypothesis, what I indicated as its implication is what we could derive from it. So what you're describing is actually to answer a different question, whether the decrease is significant, right? So that would be a different question. So let's see, we could practice it later, given the time.
Okay, thank you.
Yeah, so what you were concerned about is a different question than what this homework problem is asking for.
Okay.
All right. So let's see, what particularly what you practiced earlier is actually a different hypothesis. So if I were to answer a question whether the decrease in the average delivery time is significant, it'll be a different question. where the null hypothesis is formed this way. So that mu minus 30 is smaller or equal to 0.
Got it. Got it.
Well, actually, that would be the same question if it's formed this way. So both ways answer the, well, I mean, if we want to address your question, whether the decrease in the average delivery time, if we know previously before the joint delivery, the average delivery time is actually 30. And after the joint delivery implementation, we want to test whether the average delivery time increased or decreased, whether the average delivery time decreased at all, then this would be the null and alternative hypothesis. And after simple transformation, it will be exactly as what we just practiced. So we would still derive the same outcome or decision that we could not reject the, we would reject the null hypothesis. That means it did not decrease the average delivery time from 30 minutes.
Thanks, Jerry.
All right. So we should also understand some more about the statistical significance. I encourage you to read the links I provided, particularly about what statistical significance means, and that the fact that we could actually find statistical significance out of null patterns. And this could be more often than what we desire. And when we talk about significance, the opposite would be non-significance. And this would be a binary decision making. So there's never a more or less question. It's either or not significant. So we should not put a magnitude adjusting adjective in terms of significance. When we talk about the situation when we do not reject the null hypothesis, we should say that the result is not significant or non-significant, so that it's a clear difference from insignificant, which could be confused by many readers. So do not use insignificant, but instead non-significant when we describe null hypothesis testing. And also note that non-significant result does not mean equivalence. Statistical equivalence actually means a very different thing, which has to be decided based on an equivalence test. So I encourage you to read more about what establishes statistical equivalence. In short, statistical equivalence is when we build a 90% confidence interval limits within the, and we also take a reference to some subjectively selected equivalence bonds. This is determined by some experts. So it's not related to statistical results at all. We have to subjectively select some bonds first. If the confidence interval lies completely within the evidence equivalence bonds, then we find statistical equivalence at 5% significance level. Then we could announce that this statistical equivalence results are practically insignificant. And note that we could find statistically significant but practically insignificant effects because they are determined from different procedures. And this happens if the effect we found or the difference we found is statistically different from 0, but the effect is actually smaller than what's deemed as practically significant. All right, then let's move on to problem 2. I believe that based on what we practiced in problem 1, we should be fully equipped with all the skills we need to answer problem 2. Do you agree? Or do you have questions using what we just learned from problem 1 to address any part in problem 2?
I think solving using the spreadsheet was okay, but this part was confusing. How do you relate to interval confidence?
Oh, okay. Oh, glad that you asked. How about other students? Did you address this question in problem 2 based on, did you find this confidence interval information relevant when you address problem 2? Any cues? Okay.
Hi.
Yeah.
I'm not sure,
Yeah.
Jerry, but
Okay.
I will try.
Yeah, did you find this confidence interval information useful at all?
All I got is that I know that the confidence interval is the significance level or tolerance of making a type 1 error. I don't know how,
but okay.
I'm not sure how to connect it.
I see.
This.
Okay, glad to know. All right, let's take a look. First, I would disagree with what you described in terms of what confidence intervals means. I encourage you to read again the notes I made last week about what confidence intervals are and what they are not. Okay, so here, let's follow the notes I made in terms of the link between confidence interval and hypothesis testing. I encourage you to read the notes again after our review session because I actually supply lots of information. It might be slightly difficult to digest in a short time. So here, let's actually give a short answer so that I don't overcomplicate the things. If I were to answer this question using the confidence interval information, I would simply compare whether the reference mean lies within the confidence interval. So here, the reference population mean, which is 6 centimeters, is not inside of this confidence interval built from the sample we derive. So here, I think what's not clearly written is that this confidence interval is derived from this sample. Because 6 is not inside of this interval, I would find a significant difference so that the population mean derived from this sample is significantly different from this given average. Because it's significantly different, I would say the hypothesis test result is significant. I reject the null hypothesis. And that implies that the average length of bolts is different from 6 centimeters. Was it clear? Did you find it somewhat easier to answer than calculating all the test statistics? Yeah, okay. That's why in more recently, it's a trend that at least in academic publishing, that many visual results would include a confidence interval so that it facilitates the audience to understand immediately whether some effect is significant or not. As we just practiced, if the reference parameter we are testing against is outside of this confidence interval, we would immediately spot a significant result. Was it clear as what I just described? Any questions?
Yeah, I didn't understand.
Yeah.
any of
Oh, go
that.
ahead, Lala.
Go ahead. No,
No,
I
go.
just didn't understand. I don't have any particularly insightful question.
Okay, I think, Jerry, let me try to put that into terms that maybe we can kind of understand. Are you saying because we have the confidence interval, it's pretty obvious that the 6 centimeters doesn't fall within that interval?
Yeah, this part
Okay.
you agree, right? 6 is not inside of this interval.
No, correct. So it's pretty obvious what
Okay.
that's significant enough to give
That's-
us the answer.
And
Okay.
because of this fact, we would announce that the population, the average length based on the sample is significantly different from this reference average.
Well, it says in the question, test whether, right? Test whether the average length bolts meet the specifications.
Yeah, this actually, based on simply the confidence interval, we could actually already answer this question completely.
Okay, I get it now. Thank you.
All right, let me show you an example how confidence interval actually facilitates hypothesis testing using a plot that I made from previous projects. I will just need to find the plot that I made. Oh, okay, here. All right, in my shared screen, I shared some confidence interval plot based on previous project I made. In this study, I was trying to understand the effect of some donor milk supplementation on infant growth. I did that as a consulting project, actually by some previous student in the MBA program. Anyway, here this chart shows whether the proportion of some treatment is significantly different from 50% or not. That's why you see this 50% as the reference mean value, right? And all the confidence interval was built from the sample estimates. The red parts stand for girls, and the blue parts stand for boys. And these two confidence intervals was built from different perspective. Our regular, well, these thinner ones would be what we calculated from the regular methods. So that would be how we what the confidence intervals we derive based on. A similar but not exactly the same procedure if we use this confidence interval sheet, because I factored in that the proportion must be between 0 and 1. As you can see, none of these confidence intervals, well, actually, all of these confidence intervals include 50%, right? Because it crosses. That's why I would say, based on this chart, that none of these groups is significantly different, has a proportion significantly different from 50%. That's how you can visually use confidence intervals to facilitate hypothesis testing result by explicitly showing whether the confidence interval includes or not include the reference mean value. Any questions here? Okay, well, some advanced students could also read more about how I derived these confidence intervals from last week's notes. I believe I listed here on my GitHub, so that I derived some confidence intervals that factor in some repeated measurements, some variance difference, and I adjusted for difference comparison, and also its range preserving for both means and proportions. But I guess it might be too advanced. If you find it to be confusing, then it's okay. But this chart also shows difference adjusted. So if we look at the thicker confidence intervals, if two thicker confidence intervals overlap, for example, in this part, if we want to understand whether the male group and the female group, when their gestational duration is within this 27 or 28 weeks, because these two thicker confidence intervals overlap, then I would immediately announce that these two groups are not significantly different, because this decision cannot be directly shown by the thinner regular confidence intervals. However, this is beyond the course, so let's stop the discussion on that right there. Okay, given what we just learned about how we can use confidence intervals to derive results from a simple hypothesis testing, as we illustrated in our question, it's quite simple, but why is it? Let's take a short look. First, I want to make sure that we use the right confidence interval to answer a corresponding significant hypothesis testing question. So here, if we want to address a hypothesis testing that's two-sided at 1% of significance level, we must use a confidence interval at 99% confidence interval. Instead, if we want to address a significant a hypothesis testing question at a 5% level, we would have to use the 95% confidence interval. But all of these must be two-sided question. And so we need to confirm whether the confidence interval is one-sided or two-sided. Usually the confidence interval is given as two-sided, so we can only use this confidence interval to address a hypothesis testing that's also two-sided. So we always seek a match between the confidence interval and hypothesis testing. So I give a short procedure that you can follow. If we are addressing a hypothesis testing question using confidence interval, note that this is implicitly based on a two-tailed test about a population parameter. So that if the lower and upper 95% confidence limit, for example, in the regression summary output, does not include a 0, it implies that we would reject a null hypothesis that the true coefficient is 0. And the hypothesis test must be a two-tailed t-test at a 5% significance level. I encourage you to read more on this to understand what happens if we switch from a two-tailed test to a one-tailed test. And there's a caveat that we would have to make some alteration in the confidence interval. Given in the regression summary table, if we want to address a one-tailed question, because the given one in the regression summary output, as I indicated earlier, is a two-tailed confidence interval by default. And there's some connection between these confidence intervals and statistical tests results. I encourage you to read more, but these are not necessarily required to answer all the homework questions. All right, how about problem 3? Did you find any difficulty in problem 3?
Hey, Jerry, this is T.
Hi, T.
I definitely have no idea what to do for problem 3, if I'm being honest.
Oh, okay.
I'm over here running like a
Particularly
regression analysis. I
Okay.
don't know what I'm doing.
Ah, I see. Well, did the professor provide some videos and handouts in terms of how to interpret significance from regression models?
I haven't gotten through all the videos, so I can't answer that question honestly.
Oh, okay. Well, how about other students? Did you find sufficient information from the lectures? Any questions about problem 3 from other students that I should pay particular attention to? All right. Was that Anna? Did you have a question?
Yeah, for me, I followed the professor for part A and B. The
Okay.
part C,
Did you find it useful? Any confusion?
yeah, so for part A, I just made beta equal 0, and then that was the null hypothesis, and
Sounds correct.
then the alternative was beta does not equal 0, and then I ran the regression.
Mm-hmm.
And
Yeah,
then
that's
for
correct to me.
B, the null was beta is less than or equal to 1, and the alternative was beta is greater than 1.
No, I disagree on that. It's not, the reference mean does not sound correct. It should
Okay.
be 2 instead.
Okay, yeah, I originally had 2, but then I changed it, so okay.
Oh, okay. Interesting. Why you would change that?
Yeah,
I don't see why. Okay.
okay.
Well, let's take a look at each of these parts.
I was gonna say specifically have questions on C because I didn't answer that one, so but yeah, we can go over B as well.
Okay. So as Anna just found, she was correct in terms of how we should form null and alternative hypothesis in part A. Note that here the question in part A is there a statistical significant relationship between money spent on advertising and sales? Note here the money spent on advertising is the explanatory variable, whereas sales is the dependent variable. Here, what's asking is actually whether this coefficient estimated from the regression model is different from 0 or not. If there's a effect or relationship, then decreasing or increasing the advertising expense would make some difference in the sales. Either it's positive or negative. Translating that would mean that if the coefficient is 0, then increasing or decreasing advertising won't change the sales, the dependent variable at all. However, if the coefficient is different from 0, then there will be some consequence of increasing or decreasing advertisement. So it will make a change in the dependent variable, that's the sales. That's why we translate this question in the homework whether there's a significant relationship between the independent and dependent variable, to whether the coefficient corresponding to the independent variable is 0 or not. Do you agree on this? Any questions on this? Okay. But there's also some more I would like you to understand before moving on. Oh, okay. So if given the question listed, well, the null and alternative hypothesis we just derived from this part. If we derive a p-value smaller than the critical, than the significance level, does this suggest a causal relationship? Any tentative questions? Well, the answer is no. Although, based on the test result that's given in this p-value column, which is smaller than 5%, what we can derive is that there's a significant relationship between advertising expense and sales, but we do not know whether this relationship is causal or not. This is because the way we have this sample, it was not based on any experimental design. We did not randomly assign a low and high advertising expense across all the possible firms that we have. Instead, all these are just observational, so we could not derive any causal relationship out of an observational study design. That's why the relationship we could derive from this model is only also observational. It won't suggest any causal relationship. That means in part A, we would have a null hypothesis that the coefficient is 0, whereas the alternative hypothesis is that the coefficient is not 0. But could you help me understand, if I already observe that this estimated coefficient is 3.78, why do I need to test whether this coefficient is 0 or not? Can I just say that because this is 3.78, it's definitely not 0, so it's not 0. I reject the null hypothesis. Would I be correct if I just look at the estimated coefficient here? What's your thoughts? Oh, was it Rachana? Did you have any thoughts if I form my logic or rationale in this way?
No, actually, nothing from me, sorry.
Do you think my rationale was correct or not?
I think that coefficient would not determine if you can reject the null hypothesis or not. You need to look at standard error.
Oh, okay. Oh, well, I like your answer. So here, the reason why I cannot use the fact that what's shown in this cell is not 0, so I announce it's not 0. Or alternatively, I could say why I at all need to do a hypothesis testing is that there's standard error involved here. The standard error comes from the sampling error. So here, what we are trying to do is to find or infer about the true coefficient using a sample of 15 stores. what we want to infer is not just about these limited sample size, about 15 stores. Instead, what we try to infer is a population coefficient. That's about all possible stores that we could sample, but we did not sample all of them. Because of this limitation in the sample size, there's a sampling error. So for example, from millions of different stores, if we just sampled 15 out of them, then this estimated coefficient could be different from the true value. For example, if around all the millions of stores, if I could get access to all of them, then I could possibly get a different regression model where this observation is, millions. Then this coefficient could be, 6, or it could be 5, or it could be 2. I'm not sure because I did not have access to all the possible stores in the population. That's why the estimated coefficient here has some sampling error. And because of that, we have to use a hypothesis testing procedure if we want to infer the population coefficient. And that's why there's an error involved with the procedure, and we have to use this hypothesis testing to do it. And it will be incorrect if we just say, oh, this value displayed in the cell is different from 0, so it's not 0. Instead, we need to follow a hypothesis testing procedure. And let's see what we have to do. Once we form the hypotheses, then we calculate a test statistic. So here, the test statistic is nothing but what we practiced earlier in problem 1 already. That's the difference from the sample mean and the reference population mean. Here, it's already written in a null hypothesis. This is the reference sample mean reflected in a null hypothesis. That's 0. And we divide this difference in the two means by the standard error. That's how we calculate a t-value from a regression model. Was it clear? Is it also how you calculated a t-value? Note here, this calculated t-value coincide with what's written in this cell. So to address such a question in part A, we actually did not have to calculate again on ourselves, but understand how these t, p, and the lower and upper confidence limits are calculated. It's to address a question like this. It's a two-sided question about whether each of the coefficient is 0 or not. So for example, if we look at the intercept row, what's written in this t statistic, p-value, and confidence interval is also asking a similar question, whether the intercept is 0 or not. All right. We could also answer this question from the p-value perspective. If we look at the p-value cell, because it's smaller than 5%, so I would say we have a significant result, so that I found a significant evidence that the coefficient of advertising is different from 0. And using what we just learned from problem 2, we could also address this question from the confidence interval approach, because this estimated confidence interval for the coefficient does not include 0 in it, right? It's from 6 point, let's see, 2.56 to 5. It does not include a 0 in it. That's why I would also find a significant result based on the confidence interval approach. Do you all agree with what I did from these 3 different approaches to arrive at the exact same decision? Okay, all right. Now we understand that in regression model, also, it's nothing different from any other regular hypothesis testing. We could address a hypothesis testing question If we calculate a t-value and compare it with the critical t-value, or calculate a p-value to see whether it's smaller than the significant level, or we could use the confidence interval to see whether the reference mean is included in the confidence interval or not. With that, we could move to part B. In part B, my hypothesis has the null hypothesis that the coefficient is smaller or equal to 2, whereas the alternative hypothesis is that the coefficient is greater than 2. Do you agree with the choice of what should go into the alternative hypothesis and what should go into the null hypothesis? Okay, do you understand why I use 2 as the reference mean or reference coefficient? This is particularly because of how the question was formed. Someone claims that every additional $1,000 in advertising will increase sales by more than 2,000 in population. Because of this more than, it's a one-tailed test. Because this ratio between 1,000 and 2, that's why I use 2 as the reference coefficient. Here it's equivalent as if it asks, someone claims that $1 additional in advertising will increase the sales by $2. Note the ratio here. So that's why it's a question regarding the coefficient. The coefficient measures the conditional increase in the dependent variable given one unit increase in the independent variable, holding everything else constant. Here, because we have only one independent variable, so it would actually not make much difference if we hold anything else constant or not, because there's nothing else, right? There's only one independent variable here. But if you had multiple variables to explain the sales, for example, in addition to advertising expense, what affects the sales could also include, the location of the store, the employee size of the store, the business operation time, or the floor area of the store. If we factor in many different independent variables, what we are testing is whether holding other independent variables constant, whether investing $1 additional in advertising would bring us more than $2 back in sales. And note that I put this claim that $1 advertising expense brings us more than $2 in sales into the alternative hypothesis. By appearance, it looks like I followed a different approach as what I did in problem 1, because in problem 1, I put the original claim made by the CEO in the null hypothesis. But here in problem 3, I put the claim made by someone into the alternative hypothesis. But why? The reason is not because of what the claim is. It's based on what we try to find as the significant result. Here, the question is to find support for this claim, right? It's not evidence against the claim. No, it's formed quite differently than problem 1. In problem 1, we want to try to find evidence against the claim. Instead, in problem 3, we want to find evidence to support this claim. That's why in problem 3, if we want to find a significant outcome, this is to support the claim. So this would be in line in direction with the support that should go into the alternative hypothesis. That's why alternative hypothesis is that coefficient is greater than 2. Okay, do you all agree with how I formed this hypothesis? Actually, 2 hypotheses. Then with that, we can easily calculate a t statistic. It's nothing but the difference between the coefficient estimated from the table and the reference coefficient, that's 2. Then this difference is going to be divided by the standard error of this coefficient that's already given in the regression table. Then this would be a t statistic calculated. But we also need to find a critical t value if we want to find the decision if we based on a t value comparison. How did you get the critical t value? Did any of you use the critical t value to derive the decision? I guess it means not. So what approach did you use to address part B? Did you have any clue? Otherwise, I could show you how I derived the critical t value. Okay. This critical t value comes from the critical values sheet. So here we are deriving a one-tailed test. So we could use the t value directly from the t distribution while holding the cumulative probability as 95%. If you instead used 0.005, let's see what happens. It's a negative t value. It will be incorrect because this t value we want to compare to should be a positive value. So the critical value we are trying to find answers the question that any t value greater than this value shown in this corresponding t cell has a probability of 5% because the input is a cumulative probability. This answers the question about the probability that this t statistic is smaller or equal to than the corresponding t or the critical. But here, this t value means that this probability of t greater than this corresponding t is equal to 0.005. And this degree of freedom comes from this regression table. The residue degree of freedom is 13. That's why I put it as 13 here. Did you all understand how I derived this critical t value from this sheet? We would have to put the cumulative probability as 1 minus the significance level and 13 from the regression degree of freedom or residue degree of freedom from the regression sheet, regression table. All right. If we instead use p-value or confidence interval, we could also address this question equivalently, but it would be slightly difficult because we would have to calculate the p-value based on a correct t distribution. For example, if we try to calculate a p-value, we would have to manually change some of these input. It's not, we could not directly derive the correct p-value if we do not alter some of these cells. For example, here we want to test whether the coefficient is different from 2, right? It's smaller or equal to 2. And the significance level is 5%, but it's a right-tailed test because we have a greater than sign in the alternative hypothesis. However, what's not written clearly is what the standard deviation and the sample size is, because it's a regression table. It's not directly measured from, what's measured is a coefficient, not a sample mean. So we would have to change the sheet directly to get the correct result. So here, if we copy and paste the sample mean as the coefficient estimated from the model, and the standard deviation would, oh, I see. Well, I guess we could actually use this regression model sheet, but I haven't practiced it before. So we would have to see just now, I mean, afterwards, how I can use this regression sheet to answer this question. But to using the hypothesis test sheet to answer a regression model question would have involve changing the sample standard deviation and the sample size to some values that may not be so apparent. So here, what should go into the sample standard deviation? Oh, okay, I see. It's the standard error here. Adjusted by the by a sample size related quantity, that's square root of 14, because on this sheet the degree of freedom is what's written here -1. So the degree of freedom needs to be 13. That's why I put square root of 14 here, and the sample size -1 must equal to the degree of freedom that we require, which is 13. That's why I would put 14 here. And that shows exactly the critical t-value calculated here. Note that this calculated t-test 3.15 or 3.16 is, it coincides with what I calculated here. And the critical t-value is also exactly the same value. So that's how you could use the hypothesis test sheet to answer this question and get a p-value that's about 0.3% or 0.4%. But note that here I would have to change the sample standard deviation, sample size, to some value that may not be straightforward to understand. Okay, any questions regarding how we address part B? I just illustrated how we could calculate the t-value as the ratio between a difference in the coefficient from the reference coefficient divided by the standard error. And to compare with a critical t-value, that's from the critical values sheet. Alternatively, you could have used the hypothesis testing tab to calculate all of these directly, but it involves changing the sample standard deviation and sample size to some not so straightforward values. But we could also use this regression sheet to address this question. And okay, confidence interval for predictions in simple linear regression model, partial f-test. Well, unfortunately, it doesn't seem that this sheet answers any question regarding a regression coefficient. So easiest approach would be to use this t-distribution sheet to find the critical t-value. Was it Anna? What question did you have?
Yeah, I just wanted to mention that video, the professor uses the probability distributions tab to find the p-value. So that's the way I did it, and I just calculated the t-value, the I forgot so many names, but like the t-values, I guess, manually. So I did the 3.78 minus 2 over the 0.56, and I got the 3.156. And then for the p-value, I just used the t-distribution, and I put in 13, and then the 3.156 for x.
Oh, yeah, you could also derive that from this probability distribution part. So let's take a look at what Anna meant. So here, what this probability distribution sheet could get us is a p-value from what's calculated here. So given this, well, copy and paste the cell value, I guess. So I would have to copy and paste this cell value as the calculated t-test statistic into x in the t-distribution. Paste as, okay. Let's hope it allows copy and pasting across different sheets. Yes, it does. So I pasted the calculated t-value from my practice. That's as the coefficient minus 2 divided by the standard error to this probability distribution sheet. And using 13 as the degree of freedom, that's directly from the regression table as the residue degree of freedom. Now we find that t greater than 3.15 is this much. That would be exactly the same p-value as calculated here. But note that this could be dangerous if we, using this sheet, if we are testing a hypothesis that's two-sided. If it's a two-sided test, we would have to double this p-value. As illustrated here, this two-tailed test would have a double p-value as what's as the result in the right-tailed test. Okay, are you all clear with how we derive these results? We could, based on that, we could follow either the p-value or t-value approach, because this t calculated is greater than the critical value, so it's a significant result. Or this p-value returned from either the probability distribution or the hypothesis testing sheet is smaller than 5%. That's why we also arrive at a significant result, just as what we would have if we follow the t comparison approach. So any of these approach would work. Unfortunately, the confidence interval approach won't be so direct because this confidence interval given in this sheet are all two-sided. So we would have to use some outsource if we want to build a confidence interval that's one-sided. All right, how about part C? How did you answer this question? Part C asks for a confidence interval for a change in the sales, given a 1,000 increase in the amount of advertisement spending. Did you have any clue? What approach did you use to address part C?
My first thought when I see change, I think of in the regression model, I think of like the slope.
Yes,
So it's
sounds
the
good.
graph.
Mhm.
That's as far as I got.
Oh, okay. Well, at least you're on the right direction. So here, let's take a look of the question again to understand what it actually asks for. It's asking for a confidence interval, but this confidence interval is not a very common one, but one for change in sales. And particularly this change has to be with regard to a $1,000 increase in money spent on advertising. And I was right that this question is regarding to the coefficient again, because this coefficient of advertising measures the change in sales given $1 increase in advertising. So to answer about the measured change given 1,000 increase in advertising expense, we will simply have to times the coefficient by 1,000. So here I calculate the estimated change using the coefficient multiplied by 1,000. And this shows this value, almost 4,000, shows if I increase the advertising expense by $1,000, what would be the increase in the sales? So it gets this value. That's 1,000 times the coefficient. And to find a confidence interval for it, it's nothing but as a simple calculation as 1,000 times the confidence interval given here. That's why you see that I calculated the lower confidence limit as the lower confidence limit in the coefficient times 1,000, whereas the upper limit is also the upper limit of the coefficient times 1,000. So these confidence intervals shown here is the confidence interval of the change in sales given 1,000 increase in the change in sales given 1,000 increase in advertising expense. Do you all agree with what I did here? Any questions about how I addressed part C? Okay, now I have a bonus question for you. What would be the change given 500 decrease, a $500 decrease in ads expense? How would you address this question? If I want to ask about the change in sales, if I decrease the advertisement expense by $500.
So that whole intercept plus minus 500 into 3.78.
Ah, I see. No, it won't be that, because to answer a question regarding change, we do not have to include intercept.
Okay.
Do you understand why? Neither of the question in problem, none of the questions in problem 3 has anything to do with the intercept, because each of them is about the effect of advertising. It has nothing to do with what will happen if the advertisement is equal to $0, right? So we do not have to include the intercept at all to answer any parts in problem 3. Instead, Yeah, was it clear why we do not have to worry about the intercept in this in any parts in problem 3? Okay, all right. Because coefficient of advertisement alone, without understanding the intercept, already measures the effect of advertising on sales. Given $500 decrease in advertisement expense, the point estimate or the expected change in sales would be that negative 500 times the coefficient. So the change in sales would be a decrease by almost $2,000. We could also use the same formula to calculate the confidence interval. So given 500 decrease in advertisement expense, the confidence interval of change in sales would be this much. Do you all agree with what I just did?
Yeah.
Oh, great. Excellent. So this completes all parts in our homework. Any questions?
Jerry, just one question. How will a problem statement look if we need to use left-sided test?
Okay. Good question. Let's build on from this part, problem 3. So we are more familiar with what we already did. So if we want to form a question regarding a left-tailed test, we could test something like this. If I want to find evidence that the coefficient is smaller than 2, it would be a left-tailed test.
Okay, got it.
So you can see it clearly from my notes based on the highlighted component. If the alternative hypothesis has a greater than sign, it's right-tailed. If the alternative hypothesis has a smaller than sign, it would be left-tailed, right?
Okay.
Then what's not reviewed directly is that if the null hypothesis has a not equal to sign, well, not equal to, let me find the right symbol so there's no confusion. If it's not equal to, then we would have to use a two-tailed test. Right, okay. Now it completes which to use under what scenario. Well,
Thanks, Jerry.
my pleasure. Once we completed all the homework questions, let's review again about whether our understanding about p-values is actually what you thought it may represent. So first, we must understand that the p-value we calculated in any occasion, it's a conditional probability. But what does this conditional probability represent? It's the chance of observing more extreme estimates given that the null hypothesis is true. So note both parts. What's written under the given null hypothesis true is the condition. And the probability describing the event that we observe more extreme estimates. For example, in the regression practice we just did, all the calculated p-value, like this one, given in the regression table, that it's very close to 0, because it's a probability, right? It must be between 0 and 1. And any calculated p-value can never reach 0 and 1 directly. It must be in between. And this p-value measures what's the chance that we observe a coefficient that's at least this size in magnitude, but have a sign on both sides. If the true coefficient is 0, so it might be slightly unstraightforward to understand from the appearance. But this p-value measures the chance that could we observe a coefficient that's at least this size. So it'll be describing the chance. For example, if we could observe a coefficient that's 4 or 5 or 6, or it could be -4 or -5 or -6. It has to be on both sides because it's a two-tailed test. Then we take an integral of all these different approaches, all these different possible coefficients that's larger in magnitude than the given estimate of the coefficient. Then that's what the p-value measures. But I think what many people could got wrong is that they may not include this condition. This p-value is derived solely from the condition that the true coefficient is actually 0. The logic is if this p-value is very small, then this event is very unlikely. That's why we would reject the null hypothesis, because it's very unlikely. So because it's a p-value measures a conditional probability, it must be between 0 and 1. So this can be used as checkpoint for common mistakes. If you ever calculated a p-value or use some results as a p-value, but the probability goes beyond the 0 and 1, you know immediately that it's wrong. And we also know to guarantee that a p-value is between 0 and 1, the two-tailed test would be the two-tailed test p-value would be 2 times the smaller one in the one-tailed test p-value. For example, if we go to the sheet of hypothesis test, you find that this two-tailed p-value is 2 times then one of these one-tailed test, but it comes from the smaller one. If we use 2 to multiply this smaller one, smaller p-value out of the one-tailed p-values, then it will equal to this two-tailed test p-value. And statistical significance is claimed when this p-value is smaller than 5%, which means this event conditioned on is unlikely, so that the p-value together is very small. And the significance level, we usually take 1% or 5%, but it's also common to see a threshold as a significance level as 0.1%. It's the chance of making type 1 errors. I believe in the lectures we discussed what means by type 1 error. But let's just make a quick review in terms of conditional probability, what type 1 error means. Type 1 error is measured by the significance level that's also a conditional probability. The condition is that the null hypothesis is true, and the event is we reject the null hypothesis. That's why we consider it as an error. If the null hypothesis is true, we would make correct decision if we do not reject, right? But if we reject, the error is understood as a type 1 error. It detects significance if the, well, this error means let's see. Oh, yes. This error means that we detect a significant effect when there's truly no significant effect at all. So that the significance level is also subjectively chosen, like what we would do in an equivalence test. So it's independent from the p-value. No matter what alpha or what significance level we take, the p-value calculated will be always the same. This is apparent. If we change this significance level from 5% to 1%, you observe that, pay attention to what happens on the p-value row. You notice that it does not change. What's changed is the critical statistic. So we understand that changing the significance level won't change the test statistic or the p-value, but it does change the critical t-value that we will compare the test statistic against. All right, last part about fundamentals about p-value. Because p is a conditional probability, so a significant result, or p smaller than the significance level, does not suggest that H0 or null hypothesis is true or not. Because it does not calculate the probability of alternative hypothesis true directly. Instead, as we just learned, it's a conditional probability. It means that it's not a marginal probability. It only measures an event chance given some already known or given some other event is already true. So this is why we never say that we accept alternative hypothesis, or we do not find support for the absence of a true effect. It means we always try to find support for the alternative hypothesis. Instead, we do not seek support for the null hypothesis. All right, with that, let's practice some common myths about p-value. We already learned that from regression, a significant result does not indicate a causal relationship if the sample does not involve any experimental design, which means it does not include any random group assignment or random treatment assignment. Okay, how about this? In regression, does a p-value smaller than 5% suggest linear relationship? Based on this regression model, could you tell me whether this model suggests a linear relationship between advertising and sales?
Yes.
All right, unfortunately, it's a wrong, you got a wrong answer. The p-value smaller than 5 suggests a relationship, but it does not suggest the type of the relationship. We don't know whether the true relationship is linear or not. Alternatively, you could understand this way. If there's a parabola relationship, so the relationship is not exactly linear. For example, given $1,000 increase in advertisement, from a low advertisement fee, from 0, for example, we could get 4,000 return. But if we increase from $1,000 in advertising to 2,000, it's another 1,000 increase, but it's based on a different reference point. The estimated result could be different. It'll be apparent if we include another column. For example, ads squared. We could do that. If we include another column representing the square of advertisement spend and do a regression again, data analysis. Well, by this moment, you should be very familiar with how to do regression models, but let's practice again using 2 independent variables in this case. Well, we select sales as y and both squared and the original advertisement spending as x, claim that it has labels. I would save the output right here. So we have a left to right comparison. Note that the right model, the model to the right, would include 1 additional coefficient. Here you notice that the advertisement squared also has a p-value smaller than 5%. It means both of these coefficients is significant. It also means if we build a chart, well, actually, let's do that. If we build a chart, we should show a curve instead of a, as it shows here, we have a curve. Let me make sure it's correct. And this model shown right is what's understood commonly in our course as a second-order polynomial model, right? This would be apparent if we add a trend line and well, not linear, but well, it is linear, but I have to format the trend to include 2 polynomial, right? Yeah, order is 2. And let's display equation and R squared. All right. So we could find that this shown coefficient and model is exactly what's written here. The advertisement squared has a negative sign, whereas the linear component has a positive sign. This is exactly what's shown here in the display of the trend line of a second-order polynomial. Because if we treat this model as the true model, instead this one is an estimated one, we find that they give us different patterns, right? So here, a p-value smaller than 5 does not really suggest a linear relationship. It does suggest that there's a significant relationship, but we won't know whether it's linear or not. To address such a question, whether the relationship is linear or not, we will have to build additional orders. So it could be square of the independent variable, it could be cubic of the variable, and we add them to the model and see whether the added polynomials are significant or not. In this case, the second order polynomial is significant, so we know the relationship is at least a parabola. So $1 increase in advertising has different effects over the range of the advertisement spending. So here, the effect of $1 additional spending in advertisement has a much greater effect on sales if it's from a very small size of ad spend. But the effect could be minimal or even zero if we reach the largest size of advertisement spending, which is also why it's very important to plot the data before we do any modeling. So if we do not see this chart or this scatter plot, and we go ahead directly to a model and end up with this model, then we could miss very important second order polynomial effect if in a case that we actually plot the data, then derive the possible relationship, the most likely relationship, let's say, from the shown pattern based on the plot. So always make some descriptive analysis before doing modeling. Okay, all right. We should also note that a p-value alone does not suggest the accuracy of a coefficient estimate. The accuracy instead is represented by the standard error. But it's somewhat related to the p-value, because given the same coefficient estimate, a larger standard error would result in a smaller t statistic, which would enlarge the p-value. So it would be less likely to reject the null hypothesis, because t is calculated as the ratio between coefficient and standard error. And we would find that this standard error is different from different models because we factor in the different variation in the sample. In the first model, we do not have the second order polynomial term, and the variation only happens in this column. Instead, in a model to the right, we have two columns as the predictors. That's why the variation is different, so that the standard error and each of them would be different. And note that the estimated intercept and coefficient are both different from these two different models. So we could not derive this more simpler model directly from a more complicated model. We have to re-estimate. All right. With that, we should also learn something additional about p-values in coefficient estimate tables. As we already practiced, this t-value given and p-value given are about two-sided tests. So if the p-value is smaller than 5%, it's a binary criteria. It does not test whether the relationship is linear or not, or if the relationship is causal or not, because of what we practiced earlier. And there's no such things as an acceptable level of significance or more or less significant or pass the test, because the p-value is a conditional probability. It does not measure the probability of the conditions, but it measures the probability of extreme events given the null hypothesis true. We should also note that when there are multiple predictors, we need to discuss the result of multiple t-tests separately, one for each predictor, and keeping the model with all predictors included. And we do not develop a new simple regression model separately. That means, for example, given this model with two predictors, if we want to answer a question like whether the square of advertisement is significantly different from 0, we would have to answer this question directly from this sheet. Similarly, if we want to answer the question whether the linear component is significant, we also have to depend on this table instead of depending on a model estimated from using the original advertisement spending directly. Because as what's discussed in the note, these have to be calculated as a conditional effect. It means we have to hold some other variables constant. So when we describe this coefficient, almost 14, almost 13.5, we have to hold this coefficient constant. Hold this square of advertisement constant. All right. Holding all else constant, we would find that if p-value is greater than 5, we could not reject the null hypothesis. It means we would conclude that one predictor did not make statistical difference in explaining why or explaining the dependent variable, given that other predictors already taken account for. So that's what happens if we have multiple predictors in one regression model. When we interpret the p-values, that means whether the relationship is significant if we hold other predictors to take account for these. Okay, another for your interest is that p-value does not indicate how strong or important a variable is in explaining the outcome. If we want to find some measures about how strong or important a variable is, then we would have to instead use effect size measures. In linear regression, the effect size is measured directly by the coefficient estimate itself. But in other occasions where the coefficient may not directly measure the effect size, we would have to use some measures like variance accounted for. This is beyond the scope of the course, but otherwise these measures are understood as eta square or epsilon square. And the latter one is commonly used because it's unbiased estimate. All right, it appears that we learned, we already practiced all questions in homework and learned much additional information regarding statistical tests and p-values. Any questions? Wow.
One question before we hop off. If we're presented with a question like problem 2 on the exam for part, like for the last exam that we have for part B, is it sufficient enough for the answer to just calculate the p-value to determine whether it's significant or not? Or is it better to include the t-statistic as well?
Were you actually asking about part A in problem 2?
Oh, sorry. Yeah, problem A.
Yeah, so as I practiced earlier, you could follow either of these approaches. You could calculate a t-value or calculate a p-value or calculate a confidence interval.
Okay, so either would be sufficient enough to get like full credit basically on that question.
Oh, so to get full credit, you could follow either of these three. You don't have to show all these three.
Okay, sounds good. Thank you.
All right, this should conclude our final review session. I wish you have a wonderful weekend.
Thank you, Jerry. Have a good evening and have a great weekend.
Thank you.
Thank you, Jerry. Bye.
Bye-bye.
Bye.